Hello, I am Raffeal Bennett. I am a postdoc at the Analytical Research and Development Department at Merck in the Rahway site. And today I would like to talk to you about my current exploits with supercritical fluid chromatography, specifically with the newer pharmaceutical modalities. And let's get started. So, uh, some of the newer modalities in the pharmaceutical industry have included carbohydrates, nucleotides, peptides, proteins, polymers, and bioconjugates. Now, these analytes are very diverse in structure, many of them hydrophilic, and usually one form of chromatography doesn't cover everything. So it's important to have experts in all different forms of chromatography, despite the fact that usually you have reverse phase chromatography as your go-to. But for more polar analytes, RPLC tends to not be the best way to go sometimes. To pick up the slack on this, you have things like hydrophilic interaction chromatography. However, if you're doing purification, as you would tend to do in the pharmaceutical industry, helic methods are oftentimes difficult to scale. Furthermore, if you have more charged analytes that you want to deal with, you have ion exchange methods, which are very nice as far as using oftentimes aqueous type mobile phases. But because you have non-volatile salts involved, these methods are oftentimes not mass spectrometry friendly. And for purification purposes, you may have an additional desalting step. So one of the methods for purification oftentimes used is supercritical fluid chromatography to address these concerns. So supercritical fluid chromatography generally involves the use of compressed CO2 as part of the mobile phase. What this enables is high mass transfer kinetics and faster flow rates, which means that you'll have faster analytical methods, and this translates to faster purification, which can help you in terms of cost savings, in terms of less liquid solvent usage, because a lot of your liquid solvent is instead used as CO2, therefore faster purification and reduced waste. So usually a greener method. However, supercritical fluid chromatography, when it first began using pure CO2 as the mobile phase, was restricted to non-polar analytes. As time went on and technology grew, you had the introduction of modifiers, usually alcoholic in nature, that would be very miscible with the CO2 mobile phase. These modifiers, as you go along to more polar analytes, would include additives, sometimes water. And these additives could be acidic or basic, but some polar entity that enables a better separation. However, peptides, proteins, and nucleic acids and nucleotides still to this day present a problem for SFC that many researchers are still trying to find answers to. So with that in mind, I will talk about the polar modalities I have encountered and answers in which I have found for addressing each of these, including carbohydrates, nucleotides, peptides, and proteins. And for that last section, I will delve a little deeper into the relevance of using SFC for these separations and purification. So for carbohydrates, one of the methods I've used for this is enhanced fluidity liquid chromatography, otherwise known as EFLC. EFLC is used on SFC instrumentation, but the idea is that you tend to use a higher modifier than you would typically find in SFC. Traditional SFC methods use 5 to 50% modifier, often with methanol, for polarity. And the idea is that as you have more modifier, you have higher pressure, but you exchange that for higher elution strength, meaning that for more polar compounds, the higher modifier enables the elution and therefore separation of those analytes. Now, in somewhat recent times, people have been more exploring the use of methanol water combinations to get even more solvent strength. However, along with this, you have even more higher pressure to deal with. And in addition to that, not all proportions of methanol, water, and CO2 are miscible. And so you have to keep in mind that the exact proportions in which you mix for mobile phase when you plan to use them. However, if you're aware of the mixing region and you know where to use methanol, water, and CO2, you can exact decent separations of polar molecules like sugars, as shown in the example below. Now, EFLC has been used many times in the analytical scale, but recently I published a paper where we showed an example of using it in the preparative scale for purification. Much like you would expect for helic style or SFC style purification, what tends to happen is that the sample diluent is very important. The solvent in which you dissolve your sample prior to injection is very important to the kind of peak shape and the amount of loading that you can use on a particularly sized column. What you would expect is that as you have higher organic content in your diluent, you can usually load more and you have better peak shape. However, in the event that you are using EFLC, you are likely dealing with compounds that are relatively hydrophilic or polar. And therefore, you might find that it's actually better to use a more aqueous or even pure water diluent and instead leverage a low sample volume and high concentration because you have higher solubility of your analyte in a more aqueous medium. So it's important to keep in mind that if you use EFLC for the preparative scale, to realize that there is some fine tuning to do with sample diluent. Furthermore, based off of this work with preparative purification in EFLC, we demonstrated that the method that developed was fully amenable to mass-directed purification. Now, this is very important for SFC in that for HPLC, mass-directed purification has been around for some time. But in SFC, it's still instrumentation that is not quite universal. And so it was very impressive to see EFLC, a new method, be completely amenable with mass-directed purification. What's good about this is that you can detect non-mephoric species. So if you can't see the molecule or analyte of interest in UV, you can leverage the mass spec for triggering a purification. Furthermore, because you have a confirmed identity, a very selective identity of the analyte of interest, this allows some flexibility for separations that may not be robust, meaning retention time is shifting as you perform subsequent runs. And so with a mass-directed system, you can account for this. And furthermore, because you have a selective detector, you can be sure that what you are collecting is, in fact, the analyte of interest. So with EFLC, we are able to use mass-directed purification workflow. Now I will shift gears towards another polar set of molecules, nucleotides and pharmaceutical analogs. Now, nucleotides are known to be very troublesome in SFC. They continue to be to this day. And you can kind of see that as you look at the chemical structure of nucleotides. If you start with a simple nucleobase, nucleobases can usually be separated fairly easily on even just a traditional silica column using a methanol modifier. However, when you add a carbohydrate and turn that into a nucleoside, you'll find that you can still use SFC style conditions, but a little water goes a long way as far as improving peak shape. Now, when you add the phosphate group and you have nucleotides that you're dealing with, like adenosine monophosphate, your peak shape becomes terrible and you have a lot of trouble loading. And so even with the strategy we used for carbohydrates earlier, using high modifier and high amounts of water in that methanolic modifier, you still don't have the peak shape necessary to have a good analytical method or a good preparative method. So recently in another paper shown that if you specifically have a combination of methanol, water, and ammonium hydroxide that's finely tuned for the sake of SFC purification or analytical scale methods, you can actually elute and separate nucleotides, and particularly pharmaceutical analogs of these nucleotides. We took this even so far as to show a preparative example here where we were able to obtain the nucleotide of interest. I would like to also mention that there is a known EFLC analytical method for separating nucleobases, nucleosides, and nucleotides. However, this method does require the use of sodium phosphate buffer. So the next class of molecules I'd like to talk about, the last one, is peptides and proteins. And I would like to further delve into particularly the effect of SFC on global conformation when looking at these molecules. So proteins and peptides, again, cover a diverse set of molecules, which are all constructed of amino acids, but they can have different levels of hydrophobicity, hydrophilicity. They can have post-translational modification, and altogether be very complex molecules. In addition, you have another form of structure to deal with, higher order structure, that you typically don't see with small molecules. And this is particularly important for the pharmaceutical industry where we need drugs to remain active after purification. And part of that activity oftentimes is related to the conformation of that protein. Unfortunately, SFC in today's literature is known to cause protein denaturation. However, it's important to look at is the denaturation caused by SFC reversible, perhaps. And there are many reasons, for instance, that would cause SFC to denature a protein. Namely, could be exposure to CO2, could be exposure to high pressure, and in general, exposure to an environment that is unlike what the protein would normally see in its native form. So I'll go over a little history on the separation of peptides and proteins. One of the determining works that showed that SFC could be applied to peptides was done by Larry Taylor and co-workers. And in this case, he showed that if you use pure methanol as your modifier, you generally had very, very, very poor peak shape, unusable for analytical method design. And if you added some trifluoroacetic acid, particularly an ion pairing agent, you had much, much better peak shape that made SFC a viable technique. Later to this, I published a paper using EFLC mass spectrometry in which I separated many peptides and proteins going even as large as 80 kilodaltons for a transferrin protein that is also fairly polar. Again, I used a methanol water combination with high modifier in order to exact this kind of separation. Now, when looking at this EFLC-MS method, I particularly try to probe whether the protein was likely denatured or not. And there's a couple ways to look into this. With a protein, as it goes through a mass spec, it is ionized. And if it's folded or native, typically the charge envelope that you would see is on the low side. Whereas if you have a unfolded protein, there is more protons, ionizable protons exposed that can now be ionized by the mass spec, and therefore you'll have a higher charge envelope. In addition, you can track to see if the mass of the original protein is preserved so that the protein is in fact intact. In my work, we had determined that for the select example shown here, transferrin cytochrome C, the proteins were intact, but the charge states were rather high, indicating that there was likely some unfolding involved. Now, fast forward into a project at Merck, and we wanted to look at the use of SFC for the sake of protein purification. In this case, we devised a generic method for all the peptides and proteins we tested, using a 2 picolylamine column, 2 centimeter prep, and a special blend of mobile phase, in which the modifier was a 3:1 methanol acetonitrile ratio, with, of course, using water and TFA to enable good peak shape. The idea here is that we have a fast, high cycle time, or rather low cycle time method in which we would expose the protein to actual purification conditions. So the idea here is during SFC purification, would the unfolding that would most likely happen be reversible? For the proteins and peptides that we wanted to test, we had these 5 analytes, starting with bradykinin, which is a peptide with no order, and therefore what we put into the SFC instrument would likely be the same as what we would get out, versus myoglobin, which is a much more complex protein and may be susceptible to denaturation during SFC purification. So one of the ways in which you can probe for protein conformation is circular dichroism. Now, this is oftentimes viewed as the gold standard for determining protein conformation, and it can look at different secondary structures, alpha helices, beta sheets, and random coil formation. And in this case, we had all of our 5 peptides and proteins checked both pre and post purification, as shown in the red for after SFC purification and the black before purification. The idea here being that the profile should be roughly the same if a protein or peptide is not modified after purification. In this case, all the peptides and proteins that had order to begin with seem to lose that order, except for insulin, which, according to our theoretical helical calculation, seemed to mostly preserve its protein structure based on this kind of analysis. I will point out apomyoglobin is though the calculation shows some difference, that this difference is slight and would oftentimes need to be verified by some other method. And furthermore, even though CD spectra at a particular solvent and temperature can usually indicate that protein conformation is similar, it does not necessarily guarantee that the protein conformation is the same. So for this reason, we have CD temperature hysteresis analysis. And in this form of probing, what we do is we have a protein sample that we heat up, subject to heat, and we watch the protein unfold and take measurements at every temperature. And then we have the protein cool, and this causes some refolding of that protein in perhaps a reversible or irreversible way. But the idea is if you have 2 protein samples that are the same, then it should unfold and refold in the same manner as you elevate temperature and decrease temperature. In this example, again, insulin was the only analyte which seemed to maintain its secondary structure. And just to bring the focus over to apomyoglobin, you can now more clearly see that the pre and post purification protein has in fact changed structure based off of this analysis. Now, the third way in which you can look at protein conformation is using a technique that we've developed in our labs called size-exclusion chromatography hydrogen-deuterium exchange analysis. Now, the idea with this is that you have a protein that has ionizable protons, and you can put this protein in a deuterium oxide solvent, which allows you to deuterate these ionizable protons. And from a deuterated protein, you can then expose the protein to size-exclusion chromatography, which has a protic solvent used in it, and the protons in this protic solvent back exchange with the deuterons on a deuterated protein. The idea here is that a more unfolded protein will have more deuteration sites available for proton back exchange, and therefore you can distinguish between a more and less folded protein using the concept of delta HDX, which is basically the difference in molecular weight between a undeuterium protein, and a proton back exchanged protein. From the difference between these two, you can tell which one is more folded by the idea that a more folded protein, because it has less ionizable protonation sites, should have more deuterons contained within it, and therefore the delta HDX should be higher for that more folded protein. And conversely, a protein that is more unfolded will have a lower HDX. So for the same reason that you look at temperature changes in temperature hysteresis analysis for circular dichroism, you would look at temperature-dependent HDX analysis just to make sure that you have the same profile between two protein samples. In particular, from this analysis, we can see that, again, myoglobin clearly has different structure, both before and after purification. Before purification in black again, and the post-purification in red. An interesting situation that we detect with myoglobin is that, in fact, we see a higher delta HDX, which doesn't mean that the protein is necessarily more native, but it does mean that the protein is more compact, most likely based off of this delta HDX reading. Of these, again, insulin is the only peptide analyte that actually seemed to maintain its secondary structure or its global structure throughout this whole analysis. And so the SEC-HDX data corroborates the CD analysis data that we had determined from the previous work. So in conclusion, I hope I've convinced you that SFC can be used for a variety of applications, including the more polar, novel pharmaceutical applications that we're seeing now. Furthermore, SFC can be used with protein therapeutic molecules, but should be carefully probed for the sake of seeing if conformation changes during purification, therefore to probe viability of an SFC purification method. I'd also like to mention that of the methods that you can use for probing, SEC-HDX is certainly a method that is effective for determining protein structure after SFC purification. However, it would be best in order to use all methods for presented here for the sake of determining protein conformation. And for that, as a visual example of this, I present to you the 6-min and the elephant, for the sake of saying that each of these blind men represented here for the different techniques can give you a certain perspective of the conformation that you're trying to see. But together, you can verify a whole picture of protein conformation analysis. And with that, I would like to acknowledge my fellow co-workers who worked with me on this research at Merck. I'd also like to thank my sponsor and the MRL postdoctoral program who have made this research possible. I'd also like to thank my former mentor, Dr. Susan Olisic from The Ohio State University, for pioneering her work in enhanced fluidity liquid chromatography. And lastly, I'd like to acknowledge my postdoctoral mentor, Erik L. Regalado. Thank you, and I'll take any questions.